Hello, and welcome to the video presentation of our paper named An In-Depth Benchmarking of Text-to-SQL Systems. Nowadays, data are valuable in every domain and users from any field need to retrieve and analyze them. However, most of them have no SQL experience, and the data volume and complex schemata make the task even harder. This brings us to the text-to-SQL database search systems that allow users to explore data more easily. Text-to-SQL systems receive a natural language query over a database as input, and their goal is to translate it to an SQL query equivalent in meaning, and then execute it and return the results to the user. However, challenges arise both from a linguistic standpoint, meaning related to the natural language input, and from a technical view, which are related to SQL and the database structure. More specifically, linguistic challenges may include ambiguity, where an expression is open to more than one interpretation. For example, a case of lexical ambiguity is the word Paris that can refer either to a city or a person. The meaning of a word can also change based on the context of a sentence. For instance, when asking about the best runner, we want the one with the minimum time, but for the best nation in the Olympics, we want the one with the most medals. Paraphrasing is another case of ambiguity, where two sentences can have the same meaning but be expressed in completely different ways. For example, the question, how many people live in Texas, is equivalent to, what is the population of Texas? On the other hand, technical challenges include problems related to the expressivity of SQL, which has a more complex and well-defined syntax than natural language. For example, the seemingly simple query, return the movie with the best rating, requires a nested SQL query. Problems can also arise from the characteristics of the database. Sometimes input terms do not match exactly to database elements. For example, the user may ask for the best actress, but the database relation may be named actors. Also, objects such as names may appear in many different places in a database, as actors and directors, for example. The text-to-SQL landscape is broad, and there are several different types of approaches with their pros and cons. Database approaches can handle a variety of query types without employing neural networks, and they always produce queries that can be executed over the underlying data. Parsing-based approaches generate a parse tree that contains information about the input tokens and their relationships, which can then be mapped to query generation rules. Neural machine translation approaches have the potential of generalization, meaning translating more types of queries. However, they do not consider the actual data, so the resulting SQL, even if it is syntactically correct, it may not be executable over the data. So the big question is, how can we evaluate systems that are so different in their functionalities? Existing evaluations have some critical limitations. First, they don't use a common dataset or query set. Second, their effectiveness and efficiency evaluations are incomparable. But most importantly, they lack a query categorization for a fine-grained comparison of each system's main functionalities. WikiSQL and Spider are two famous text-to-SQL datasets, but they both have their limitations. They both measure effectiveness based only on the number of queries translated to SQL, and they do not provide any refined query categorization. But to build better text-to-SQL systems, as well as combine the best of the existing approaches, we need to understand the capabilities of the systems in depth. For this reason, we introduce a new query benchmark designed for the purpose of testing query expressivity. Through our experiments, we analyzed the query expressivity of each system, their disambiguation process, the efficiency of the systems in regards to the total execution time for each query and the resource consumption, and finally, their potential for scalability. In the rest of the video, we will present the different approaches to the text-to-SQL problem, describe our benchmarking approach, and discuss the results of our experiments. Let's start by explaining the different approaches to the problem. In database approaches, a query answer is defined as a subgraph of the database schema, where the nodes represent the relations and the edges the joins between them. These approaches employ the inverted indexes of the database in order to map the input query keywords to the database entities, and the database schema to find the joins between the relations discovered in the query. Parsing-based approaches parse the input query generating a parse tree and use that to understand its grammatical structure. The tree nodes correspond to database entities and operations such as filters and aggregate functions, while edges define the structure and the order of the operations. Similar to the database approaches, they use the database indexes and the schema, but they also use a parser in the initial phase to extract the relations between the keywords. All systems follow a similar general architecture, which is shown in the figure on the right. First, the query passes from the parser if it exists, and it is transformed to a more structured format, such as a tree, for example. Then, the entity mapper receives the input terms and matches them to database elements with the help of the indexes and knowledge bases. The interpretation generator extracts query operations such as joins, aggregate functions, and comparisons, and creates another structured format that represents the order and the dependencies of the operations. As we have mentioned before, due to the ambiguity, several interpretations may be generated for a query. Then, the SQL translator and executor uh, uh, translates the interpretations to SQL and executes them.
We focused our analysis on database and parsing-based approaches, further categorizing the systems based on the type of the input they accept. Keyword systems accept queries containing simple keywords like drama movies. Enhanced keyword systems can handle queries with more sophisticated keywords like aggregation functions. And lastly, natural language receive natural language queries exactly as in conversations between humans. Keyword systems act like search engines and search the keywords they receive in the database elements. Discover, for example, generates a query interpretation as a subgraph of the database schema graph. Discover AR builds on Discover and adds information retrieval style ranking heuristics to enhance the term disambiguation process. And Spark introduces improved ranking and execution methods. The enhanced keyword systems impose syntactic constraints on their input to support aggregate functions, group bys, comparison operators, apart from simple queries. ExpressQ looks for specific keywords in the input that trigger aggregate functions and group bys. SODA, in addition to the above functionality, expands the system's knowledge with other sources, like domain ontology. The most sophisticated system category in our analysis are natural language systems. The main idea behind such systems is to use a parser to understand the relationship between the keywords in the input and allow for a syntax restriction-free query. Nalir uses a syntactic parser to understand the query structure, then maps the parse tree nodes to database entities, and finally translates the tree into a valid SQL query. Now we will present our benchmarking approach. Our goal was to build a single benchmark that we can use to evaluate all our systems. Therefore, it should capture different cases of text queries, such as keyword and natural language. It must also have queries that cover both linguistic and technical challenges. To enable a fine-grained comparison, we have grouped the queries into categories, where each category evaluates a single independent expressivity aspect. To design our query set, we first enumerated the basic set of query sketches and started to expand following these rules. Each category should cover a different SQL query class, for example, aggregation, group bys, etc. Then we added extra categories to emulate the human factor, like typos and synonyms. And lastly, we should respect the input constraints of each system where it was possible. To fill those categories, we tried to avoid overlaps between categories as much as we could. Queries within categories should be diverse. And lastly, we preserve the same number of queries per category and use uniformly the databases in each category. We ended up with 17 categories consisting of around 240 natural language queries, which can be roughly divided into two groups. SQL expressivity challenges, such as queries with join, aggregates, and group bys, and natural language challenges, such as queries with terms that are synonyms to database elements or even misspellings. Lastly, we will show our experimental results. We measured the effectiveness of each system across all categories, which is defined as the number of correct queries divided by the total number of queries. Since most systems return multiple answers ranked based on their own scoring scheme, We manually checked if a correct answer was among top 1, top 3, or top 5 of the system answers. We found that no system shows consistently good performance across all categories it covered, and that there is little to no coverage of final challenges, which are also harder. Natural language is inherently ambiguous, so the systems try to narrow the possible answers by applying disambiguation techniques, while preserving some kind of diversity among their answers. We saw that some systems have stricter disambiguation methods, while some others tend to allow more diverse answers. Efficiency is also important for text-to-SQL systems. Regarding the execution times for a query, we measure the time it took each system to generate the SQL translation with and without executing them against the database. First, we want to see how fast the systems are, but also how efficient the queries they produce are too. We also monitored the execution time of every system component to identify bottlenecks. For the resource consumption, we measure the CPU utilization, main memory usage, and the number of SQL IOs. We have noticed that both are tightly coupled with the database and query characteristics. If a database has more unique values, the indexes are more stressed. If we have more join possibilities, the exploration space is larger. By exploring the dataset characteristics used in our analysis, we can get a better intuition about the performance of the systems. As mentioned before, we used three databases, namely IMDb, MAS, and Help. Analyzing their structure, we see that IMDb and Help follow a star-like schema, while MAS is more of a mixed structure. Queries in IMDb and MAS use between 2 and 5 relations, but for the latter, most of the queries use 3 to 4 relations. This means smaller exploration space and thus better efficiency. If we dive deeper and analyze the terms used in the queries, we can get some useful insights too. If terms appear in multiple locations in the data, then we increase the complexity of the entity mapper, and thus the error rate is higher. For example, MAS has the lowest mappings per term and the most unique terms per query. This puts less stress to the entity mapper, lowers the exploration space, and provides better results. Finally, through our experiments, we conclude that complex queries containing misspellings, negations, and complicated logic still remain an open challenge. Additionally, we saw that our systems cover different query types, so one could combine them to benefit from their strong points. Also, there are no universal solutions because different datasets present different intricate characteristics. And lastly, we need the right balance between diversity and disambiguation, given the fact that query subjectivity allows for diverse answers. More results and insights is in our paper. Thank you very much.